So let's take a look at some examples of finding the Laplace transform on functions that involve the step function. So as a reminder, if we want to take the Laplace transform of some function that has been translated a units to the right times the step function that has been translated the same amount, then the way we do that is we multiply e to the negative as times the Laplace transform of just the function f. So remember, f of t, when we do the Laplace, transforms into big F of s. So as long as these horizontal translations are the same, then we just take whatever our function f is, we transform it, and we multiply it times e to the negative as. Now, it's not always going to be that the step function and our base function have the same translation. So in general, if we have some function times u of t minus a, then when we take the transformation of that, it's still going to be e to the negative as, but we're going to take the transform of that function at t plus a. So whatever our original function is, if we don't have the same translation in it and the step function, then we have to find out what is that function evaluated at t plus a, transform that, and then multiply it times e to the negative as. So let's take a look at this example here. We want to transform t squared u to the t minus 1. So our function that we're transforming is t squared, and our step has an a value of 1. So basically our switch turns on at 1, and from 1 to infinity our switch is on. From 0 to 1 our switch is off. So notice the input here and the input there are not the same. This one is 1 unit to the right farther than this one is. So since they don't have the same horizontal translation, then we use this property down here. So our a is 1, so we need to find g of t plus 1. Well, how do we do that? We substitute t plus 1 into the function g. How do we do that transformation? Well, we have to square that out because we don't have a transformation of a chain of a composition. So we square that, t squared plus 2t plus 1. So our transformation is going to be e to the negative a times s times the Laplace transformation of this function, t squared plus 2t plus 1. That's what this says here, e to the negative as. Once we have added our variable and computed g of t plus a, we transform that. So what we're going to get, we're going to get e to the negative s times, when we transform t squared, that's going to be 2 factorial over s to the 1 greater power. When we transform the next one, we have 2 as a coefficient. That's going to be 1 factorial over s to the 1 greater power. And when we transform 1, we get 1 over s. Of course, 2 factorial is 2, 1 factorial is 1. So e to the negative s times 2 over s cubed plus 2 over s squared plus 1 over s. That will be our Laplace transform of the function we were given. All right, let's take a look at this one. So our function is t plus 2 squared. Our step is u of t minus 3. So in this case, a is 3. So to take the transformation of that, it's going to be e to the negative as times g of t plus a. And let's be careful, is the transformation of g of t plus a. So in our case, a is 3, so e to the negative 3s times the transformation of g to the t plus 3. So what is g of t plus 3? Well, if g of t is this, g of t plus 3, we put a t plus 3 where we have a t. So we're replacing t with t plus 3. So that gives us t plus 5 on the inside. And then as we did in the previous example, we have to square that out. So t squared plus 10t plus 25. So our transformation will be e to the negative 3s times the Laplace of t squared plus 10t plus 25. So that's e to the negative 3s times 2 factorial over s to the third plus 10 times 1 factorial over s squared. And when we do the transform of the constant, that's times 1 over s, or we do 25 over s. So that's our transformation. Notice the inputs did not match there, so we couldn't just do e to the as and then the transformation of our base function squared. We had to translate it essentially to make our inputs work together. All right, as we do an inverse Laplace, let's remind ourselves that the translation property said that if we do the Laplace transformation of f of t minus a u of t minus a, that translates into e to the as times the Laplace of that function. Conversely, the inverse Laplace of e to the negative as times f of s transforms back into f of t minus a times u of t minus a. So if we look at our transform, we're trying to transform e to the negative 2s times 1 over s squared. So in our case, this is e to the negative as, and this is f of s. So our a is 2, our f of s is 1 over s squared. So if we can get the inverse Laplace of 1 over s squared to get f of t, then our answer will be that function at t minus a times our step at t minus a. So how do we inverse Laplace 1 over s squared? Well, if we look at our table, then this resembles n factorial over s to the n plus 1. So n plus 1 corresponds to 2, which means n is 1. And where does that come from? That's transforming t to the n. So f of t transforms into t to the first. We have 1 is 1 factorial. We have s squared on bottom. So as we said, that makes n 1. 1 factorial over 1 plus 1. So n is 1. So that's the transformation of t to a power, so t to the first. So that's f of t. So when we go backwards, we need f of t minus a, where a is 2, times u of t minus 2. Well, if this is the function for f, then if we plug t minus 2 into that, we get t minus 2 times u of t minus 2. So that's the inverse Laplace of that particular function. So let's take a look at another one. If we want the inverse Laplace of this, then let's rewrite this as e to the negative 3s times 1 over s squared plus 9. So this is e to the negative as, and this is f of s. So if we take the, and don't forget our inverse Laplace. So remember, when we take the inverse Laplace of that, it's f of t minus a times u of t minus a. So in our case, a is 3. F of s is 1 over s squared plus 9. So if we look at our transforms in the table, this seems to be similar to b over s squared plus b squared. So our b is 3. So if we have we need a, if that's 3 squared and we have a constant on top, that constant needs to be 3. So we need to pick up a 3 out front. So that's 1/3 times 3 over s squared plus 9. So to get f of t, we need to take the inverse Laplace of that. So if we have a coefficient, we can leave the coefficient out front. And then we can transform the function part. So that transforms into sine of b times t. So that's f of t. Remember, our answer is f of t minus a, or in our case, f of t minus 3 times u of t minus 3. So what is f of t minus 3? If this is f of t, f of t minus 3 is 1/3 sine of 3 times t minus 3. So our transform is 1/3 sine of 3 times t minus 3 times u of t minus 3. Let's look at another. Let's look at this one, and let's find the inverse Laplace of this. So let's rewrite this as e to the negative 3s times s over s plus 2 squared plus 1. So this is our e to the minus as, and this is our big f of s. So remember, if we're transforming that, what does that transform into? That transforms into f of t minus a, u of t minus a. So our a is 3. We need to find out what is the inverse Laplace of that function. We need to inverse Laplace s over s plus 2 squared plus 1. That will give us f of t, and then from there we can get f of t minus a. So how are we going to do our inverse Laplace here? So we have two formulas that involve an s squared plus b squared. This is the one that has the s on top. So if we have an s on top, then it has to match this. So if we have a plus 2 there, we have to also have a plus 2 here. If we add 2, we also have to subtract 2. So I'm going to put that minus 2 on its own fraction. Notice these have the same denominator, so we can add these together. So we have s plus 2 minus 2, so those cancel, but we need that plus 2 to make those match. So this first term, when we do the inverse Laplace of that, table, when we have, in this case, this is a different a, but this a is negative 2. When we have e to s minus a plus b on bottom, s minus a on top, then that transforms into the e to the at cosine of bt. This is b squared, so b is 1. So that's what the first term transforms into. if we have a constant on top, remember this is b squared, so we need a b on top. So that 2 we just pull out front. And when we have b over s minus a squared plus b squared, that transforms into e to the at sine t. So that's our f of t. Remember, that is big F of s. When we transform that back, that becomes f of t. So our answer, remember, is f of t minus a, where that a is 3. So we need f of t minus 3. So in that function, everywhere we have a t, we replace it with t minus 3. So e to the negative 2 times t minus 3 cosine of t minus 3 minus 2 e to the negative 2 times t minus 3 times sine of t minus 3. So that's f of t minus 3, and then all of that gets multiplied times u of t minus 3. So we could just copy this. So our final solution is that times u of t minus 3.